Bismillahirrahmanirrahim. Welcome back in class of real analysis. Hello students, I hope you are all keeping well. In today's short lecture, we will state and prove a very important inequality, that is Schwarz inequality, and sometimes also called Cauchy Schwarz inequality. Here we are going to prove this inequality for complex number, although this inequality also hold for real numbers, and this is uh, actually theorem 1.35 in Walter Rudin textbook. If A1, A2 up to so on An and B1, B2 up to so on Bn are the complex numbers, then this inequality says the square of absolute value of sum of product, that is summation Aj into conjugate of Bj, is less than or equal to the product of sum of squares. This is the sum of squares of absolute value of Aj, and this is the sum of square of absolute value of Bj, where A and B are all complex numbers. So to prove the inequality, we labeled or assumed these numbers by, let this number summation j is equal to 1 to n is denoted by capital A, and this is denoted by capital B. You can notice that this is a real number because here the absolute value, that is also called the modulus, is always a real number. So this is the Aj absolute represent the absolute value of the complex number Aj, or the modulus of complex number, that is always a real number. So suppose this sum is denoted by capital A and this sum is denoted by capital B, and A and B both are the real numbers here, while this summation is actually a complex number because this is not a absolute value, this is only the product of the complex number Aj and conjugate of Bj, and suppose this is C. I will prove the inequality in two cases. If B, that is summation j is equal to 1 to n square of Bj, this is equal to 0, then this is possible that if every b1, b2 up to some bn, this all of these complex number are 0, because if you open this sum, you can write it as b1 absolute square plus b2 absolute square up to so on bn absolute square, which is equal to 0. So this is the sum of square. This represents sum of squares of positive non-negative quantities, and if this is equal to 0, it is possible that itself b1, b2 up to some bn, these are all 0. So in this case, conclusion is trivial. In other words, if you put all of b1, b2, bn equal to 0 in the inequality, when you put here every value, every b equal to 0, then this sum becomes 0. Similarly, when you put every b is equal to 0 on the right side, then this summation is also equal to 0. So the this inequality hold. Suppose next we assume that b is positive. Why we are not taking the case b is less than 0? Because this is not possible, because b is the sum of, because b is equal, b represents the sum of squares which cannot be negative in any case. So that's why we are only assuming the case when now b is greater than 0. If b is greater than 0, then we have to show that c square is less than ab. How can I get this inequality? When we assume this product is c, this becomes square of c absolute. This should be less than equal to, if this is my a and this product, this sum represent b, so this shows that c square is always less than equal to ab. Okay, To prove this inequality, we will consider this quantity. You have to remember this quantity in the whole proof. This is b time aj minus c time bj, and as aj and bj are the complex number, so clearly this difference is also a complex number. This is a complex number, and you know that square of z modulus or z absolute, where z is a complex number, is equal to z into z conjugate. So by using this result, we can write it as this is my complex number and this is its conjugate. Now applying the conjugate on this term, we can write it as, by separating the conjugate, this becomes b time b into aj conjugate and c conjugate bj conjugate. As above I have discussed that a and b, these are the real numbers, but c is a complex number. C is actually the product. This C is a, this is my C. That is the sum of the product of complex numbers. So this is the complex number. C represent a complex number, but A, which is the summation of the square of absolute values, that is always a represent a real number. This is also a real number. So that's why we will not take the conjugate over A and B. So this becomes, now we multiply the terms we have. Now multiply the first term of that is BAG with BAJ conjugate. We have B square AJ into AJ conjugate. Similarly, multiply the remaining terms. We have BC conjugate AJ into BJ conjugate. When we multiply this term, these two terms, we have minus BC into AJ conjugate into BJ. And lastly, we have C into C conjugate, BJ into BJ conjugate. Again, using the property that Z into Z conjugate is equal to Z modulus square. So the product of these two terms can be written as square of AJ. And similarly, the last term, this term, can also be written as BJ conjugate, BJ modulus square, as C is a complex number and this is the product of C with its conjugate, so it also can be written as C modulus square. Now taking summation on both sides at each term, over each term, this was my left side, so I have B square into summation j is equal to 1 to n AJ square up to so on. Now substituting the value of A, B and C, this is the important step here that you can notice here. This is my A, so I will replace this with A, and this is my B, so I will replace this with B, and this is my C. This summation is my C, but this is not C. In C we have conjugate over B, but in this summation we have conjugate over A. So next we write this as, this is the first term B square A, and this is the last term. Now these are the important terms that you can notice here. This term can be written as B into C conjugate, and this is my C. So this becomes B into C conjugate into C. But if you notice here, this summation that is the product of the complex number is actually the conjugate of this number. I have written here, this is my C, and if you take its conjugate, then C conjugate is equal to this summation. because here A and B are the complex number. When you take here the conjugate, we will take we have a conjugate over A, and the double conjugate over B becomes simply Bj. So I will replace here this term with the C, this summation with C, and this summation can be replaced with C conjugate. So we have two terms, minus B into C conjugate, and this term can be written as minus B into C into C conjugate, that you can see here. Next, as C into C conjugate is equal to square of modulus, so this can be written as minus B into C modulus square, and similarly this can be written as, and this is my B times C modulus square. Cancelling out the like terms, we have remaining two terms, B square A into minus B times C modulus square. Now taking B as a common factor from these two terms, this becomes B into A minus C modulus square. Suppose this is star. In star, the term on left hand side, what is my left hand side? This is my left hand side, and its answer is this. Now in the left hand side, you can see here, this is the modulus or the absolute value of complex number with square. So this cannot be negative. This will be always greater than or equal to 0. In star, the term this is always greater than or equal to 0. Hence, we can say that the right hand side, that is B into B A minus C square, is also greater than or equal to 0. Next, as we have assumed that B is positive, because this is our case number 2, and in case number 2 we have started our discussion with the supposition that B is greater than 0. So here B is greater than 0. So if B is greater than 0, and this is the product of two terms, which is also non-negative. Suppose I have a product x into y that is greater than or equal to 0, and I am confirmed that x is greater than 0. It must be that the second term y is greater than or equal to 0. So if this is my y and this is my x, and x is greater than 0, and the whole product is greater than or equal to 0, this implies BA minus C modulus square is greater than or equal to 0, or I can write it as AB greater than or equal to C modulus square, or C modulus square is less than or equal to AB, which is required, that we have to show. So I hope this is my this lecture is helpful for you, and now you have a clear understanding about the concept of Cauchy Schwarz inequality. Inshallah, in the next lecture, we will discuss accretion spaces and the properties of norms. If you find my lectures helpful, kindly like, share, and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.